Okay, thanks a lot. So I'm very happy to be here today to give this talk. So what I'm going to be talking about is based on a work that I did with Ewan Gwynn a few years ago. So Ewan is currently based in Chicago, but actually when we did this, he was in Cambridge as a postdoc. Okay. Okay, so what is this talk about? So the main question which motivates this work is how one goes about making sense of what would be the canonical probability measure on the space of surfaces in the same way that we can think of Brownian motion, one of our good friends in probability theory, as the canonical measure on the space of paths. So this is what a Brownian motion looks like in 2 dimensions. And this is now my favorite picture of what one of these random surfaces looks like when it's been embedded into 3-dimensional space. Okay, and in this topic, there are actually 2 different approaches which have been developed to address this problem. So there's one which is based on approximating these surfaces using discrete approximations, and this has its roots in the combinatorics literature, looking at planar maps. And then there's also a continuum approach, which has its roots in the physics literature, and this is Liouville quantum gravity. So what I'm going to do now is I'm going to explain to you one way of thinking about where this construction, Liouville quantum gravity, comes from. And this is sort of the natural way to think about constructing a random surface if you're like a geometer or somebody from complex analysis. And the starting point is the classical uniformization theorem, which says that if you have a 2-dimensional Riemannian manifold, which is simply connected, then you can always conformally map it to either the disk, the plane, or the sphere, whichever one it happens to be topologically equivalent to. And the really nice thing is that if you use this conformal mapping as a chart for your surface, and then you take the Riemannian metric on your surface and you use this chart as coordinates, then the metric takes a very simple form. It's just given by the Euclidean metric, and then in front of it, you have this factor e to the rho of z. This is the conformal factor, where rho is some smooth function. And what this means, or one way of thinking about it, is this gives you a way to parameterize the space of surfaces, which are homeomorphic to the disk, the plane, or the sphere, in terms of the collection of smooth functions on your domain. And very simply, how does this work? If you take your function just to be the 0 function, you're going to recover the surface that you started off with. And more generally, if your function has 0 Laplacian, then you're going to describe a surface which has a flat metric. And if you want to use this as a starting point to develop a theory of random surfaces, what you have to do is you have to decide what probability measure you're going to put on the conformal factors rho, and what is the natural way to do that. And one way of thinking about it is if we want to have some random surfaces which are somehow like the natural randomly fluctuating metrics about the flat metric, it's somehow natural to take your rho to be the sort of canonical perturbation of a harmonic function. Again, because when your function is harmonic, you're describing a surface which is flat. And in probability theory, there's an object which is the canonical perturbation of a harmonic function. And this is something called the Gaussian free field. The Gaussian free field is a field, a random Gaussian field, which in this case is defined on a planar domain D. And because it's Gaussian, you just have to describe what its covariance function is. And in this case, it's something very nice. The covariance function is just given by the Green's function for the Laplacian on your domain D. And because the Green's function is conformally invariant, the Gaussian free field is also conformally invariant, and it has lots of other nice properties. In particular, it's also a Markovian random field. And it comes up in lots of different places in probability theory. And the reason for this is that there are many central limit theorems which say that the Gaussian free field describes the fluctuations for different types of height functions. It also comes up in random matrices and lots of different things. But here, the reason that it's important is that in a certain sense, you can think of the Gaussian free field as being the canonical perturbation, random perturbation of a harmonic function, because there's a nice informal way of describing what it is. And informally, you can think of the free field as the random field which has this density, which is given by e to the minus the Dirichlet energy squared of your function divided by 2. And this is the density with respect to what you could think of as being, the uniform measure or the Lebesgue measure on the space of functions on your domain. Now, of course, this does not really make sense because there isn't really a uniform measure on the space of functions, but it's actually not that difficult to nevertheless think of the Gaussian free field rigorously in this way. And the reason that this allows you to think of it as the canonical perturbation of a harmonic function is that, if you look at some class of functions, then, with some given boundary conditions, then the one which minimizes this energy is just going to be the harmonic extension of the boundary conditions. Now, one sort of tricky thing that makes the mathematics about what I'm going to talk about interesting is that the Gaussian free field in 2 dimensions is not an actual function. It's only a generalized function. And one way to see this is that if you look at the covariance function, which is given by the Green's function for the Laplacian, and you remember that we're in 2 dimensions, the way that it behaves is it behaves like minus the log of the distance between your 2 points. So this in particular blows up as x goes to y, and so this field has infinite variance at points. And this is the reason that it's not really a function, it's rather a random variable which takes values in the space of distributions. Okay, so again, what I'm talking about is we have this goal of trying to make sense of what would be the canonical model for a random 2-dimensional Riemannian manifold. And Polyakov, back in the 1980s, who was working on string theory, said that a very natural thing to do is to take the Euclidean metric on some planar domain and then form a random surface by perturbing it by this conformal factor, e to the gamma h, where h is a Gaussian free field on your underlying domain, and then you have this parameter gamma, which can be between 0 and 2. And what the gamma determines is the strength of perturbation from the Euclidean metric. So if gamma is equal to 0, this is just the Euclidean metric. And as you make gamma larger and larger, it's a bigger and bigger perturbation of the original Euclidean metric. And the difficulty, or the thing that makes this interesting to try to study, is that this expression here doesn't really make any mathematical sense, at least without some additional interpretation. And the reason is that the thing that we're exponentiating involves the Gaussian free field, and the Gaussian free field is a distribution, not a function, and so a priori its exponential is not defined. Over here on the right-hand side, I have a couple of pictures which are to give you a sense as to what these Liouville quantum gravity metrics actually look like for different values of gamma. And what they show are the square, and then what I've done is I've subdivided the square into dyadic squares, where each one has approximately the same size using the random metric. So when gamma is larger, you see this effect much more pronounced, where you have some very big-looking dyadic squares, like this one here, and then you also have some very small, sort of microscopic black dots. And even though these have very different Euclidean sizes, they have approximately the same size with respect to the random metric. And this is indicative of the fact that these are fractal surfaces. They're not going to be something which is smooth. And one of the reasons that probabilists got interested in this area is that there were some conjectures that were floating around for a while that said that these Liouville quantum gravity surfaces were supposed to be the right continuous object to look at if you wanted to describe the scaling limits of some discrete surfaces which come from the theory of random planar maps. Okay, so here's one more picture. So this is a Liouville quantum gravity surface where the value of gamma is given by the square root of 8/3. This turns out to be a very special and important value of gamma. And what you see here on the slide is a picture of a metric ball with respect to this random metric. The center of the ball is right here. And the different colors that you see, they just indicate the distances of different points inside of the metric ball from the center. And I've also superimposed on top of the metric ball all of the geodesics inside of this metric, starting from the outer boundary and going back to the center. And one of the things that you see here is something which is very important and useful in the subject, which is called the confluence of geodesics phenomenon. And basically what this refers to is that if you look at different geodesics, what they like to do is they come together and they merge, and then they form this, this tree-like structure. So in particular, when you look at this picture, it doesn't look like that there are actually that many geodesics there, but what's happened is that most of them have merged before they get very far away from the boundary. Yep? The color white are points which are not inside of the metric ball. So these metric balls, the complement is not simply connected. There's actually going to be a countable collection of holes. And again, this is reflective of the fact that these things are very fractal objects. Yes, and the confluence of geodesic phenomenon, it's something which comes up a lot in fractal geometry, and it's something which is actually really important and useful in practice for proving things about these objects. Okay, so that was a very quick whirlwind tour of the continuous theory. Now I want to talk a little bit about some of the motivation which comes from the discrete theory. And the starting point here are what are called planar maps. So a planar map is just a graph together with an embedding in the plane so that no two edges cross. A planar map is kind of like a planar graph, but actually the difference is that you have a slightly different notion of equivalence for planar maps versus planar graphs. So for two planar maps to be equivalent, you have to be able to deform the plane in a continuous manner to take one to the other, which is not quite the same thing as just being isomorphic as graphs. And in this particular picture, I've made a quadrangulation, which just means that each of the faces here are exactly quadrilaterals. And the idea is that a planar map can somehow correspond to a surface where what you do is you identify with each quadrilateral a copy of the standard Euclidean square, and then you just glue the squares together according to the adjacency structure of the map. So how does that work? And perhaps a simpler way of thinking about this. So you can imagine starting off with a sheet of paper, like this one here, and then you get out your pen and your ruler, and then you divide the sheet of paper into squares which have equal size. So in this case, I have 12 of them. And then you get out your scissors, and you cut your sheet of paper into 12 small copies of the standard Euclidean square. And then you get out your bottle of glue, and then you just glue the boundaries of these things together in such a way that you get a surface. And it's very nice if you take your surface to be homeomorphic to the standard two-dimensional sphere. And the way that this corresponds to a planar map is that you use the adjacency structure of the map to decide which boundaries of the squares to glue to each other. And if you've done it properly, you get a picture which looks like this. So this is a little origami which shows a planar map made out of paper. It actually might not look like this is a quadrangulation because you see some pointy things here that actually look more like triangles rather than quadrilaterals. But all that's happened is that when you take these quadrilaterals, you're allowed to glue like two edges of the same quadrilateral together. And when you do that in three-dimensional space, you get something that looks like a triangle. And then it's a very interesting mathematical question to understand what do random quadrangulations actually look like when you pick them from some probability measure and you let the number of faces go to infinity. And this is a question which has a long history. In a sense, it goes back to work of Tutt back in the 1960s. So Tutt was interested in the problem of enumerating planar maps because he wanted to try to prove the four-color theorem. And one way of doing that would be just to enumerate all possibilities and see that they satisfy the four-color theorem. He didn't succeed in that, but what he did succeed in is proving lots of formulas which count different types of planar maps. And the formulas, in many cases, are surprisingly simple. So this one here, this one counts the number of quadrangulations that you can form, which give you the topology of the sphere and have n faces. Okay, so this picture here, this has a relatively small number of faces. What does a big one look like? Well, so here's the same picture that I showed you before. So this is a quadrangulation which was chosen uniformly at random. And this one, I believe, has 1 million faces. And then it was embedded into three-dimensional space using something like spring embedding. Now, when you do these kinds of embeddings, these are not isometric embeddings. So distances get distorted quite a lot. But I think that these kinds of pictures are still really useful to look at because they remind us that when you pick these kinds of surfaces at random, you're going to get something which has a fractal structure. It's not going to be a smooth metric. It's going to be something very rough. And this is my new favorite picture of these types of things, and these were made by Benedict Stuffler. Okay, so in the subject, the study of random planar maps in the probability literature became to be very hotly studied, going back about 20 or so years. And people wanted to understand, how you take scaling limits of these types of objects. You can view these things as metric spaces. So you have a random metric space and then ask about what type of metric space scaling limit you could get. And for maps chosen uniformly at random, the first thing that you would want to know is what is the typical diameter of a planar map, a quadrangulation with n faces. And it turns out that it behaves like n to the 1/4. This exponent was computed by Schesing and Schaefer. And then it was shown by Jean-François Le Gall that if you take your planar map metric and you rescale it by the typical value for the diameter, which is n to the -1/4, then you get something which is a tight sequence of metric spaces. So this is probabilist jargon saying that you have subsequential limits. It's a compactness result. And it took a long time before people were able to go beyond this tightness result, but there were lots of very interesting results which were proved in the intervening period. In particular, for the subsequential limits, which are random metric spaces, it was proved by Le Gall that they always have Hausdorff dimension 4, so they're 4-dimensional as metric spaces, but at the same time, they are homeomorphic to the 2-dimensional sphere. So this last result was proved independently by Le Gall and Paulin and Meermont. So what this means is that if you look over here, on the right-hand side, left-hand side, you see a lot of like spikes and regions which look like they're about to be disconnected by bottlenecks. Really what happens in the limit is that these things don't pinch off and you get something which still has the topology of the sphere, but it's 4-dimensional in the Hausdorff dimension sense. And then one of the big results in the area came about 15 years ago, where Le Gall and Meermont, who are both working on this problem, they showed that it wasn't necessary to take a subsequence in order to get convergence. You really do have a real limiting object, and this is something which was called the Brownian map. The reason that it's called the Brownian map is that there's an explicit description of what the limiting object is, and it can be built out of Brownian motions. So that's the Brownian part, and where map comes from is, well, because it's the limit of planar maps. And since then, there's been a whole theory of what are called Brownian surfaces, which have been developed. And where these things come from is when you take scaling limits of planar maps with other topologies. So you don't have to start off with the sphere topology. You can also do this with the disk topology, the plane topology, the half-plane topology. You can also have surfaces with positive genus, and they all have continuous limits that you can describe. And actually now, because there's the whole zoo of Brownian surfaces, people often refer to the Brownian map as the Brownian sphere because it's the one with the topology of the sphere. And one thing that I want to emphasize is that from this perspective, the kinds of objects that you get are abstract metric measure spaces. And the reason for this is that the type of limit which is being taken is in the Gromov-Hausdorff topology, and what that encodes are distances. Okay, so this is a random variable which is like a random metric space which happens to be homeomorphic to the sphere in the Brownian sphere case, or one of these other topologies if you started off with something different. Okay, so I've talked about these two different theories of random surfaces, and there were these conjectures that were sort of floating around going back into the 1980s, which says that they're supposed to be the same thing. So, one way of describing the continuous limit of a random planar map would be in terms of this, this type of Riemannian metric in the plane, if you could make sense of it. And the different values of gamma, they depend on what type of random planar map model you start off with. So you get the value gamma is the square root of 8/3 if you chose your map uniformly at random. And this is what one of these guys looks like. And for other values of gamma, you get other types of planar maps. So in particular, the value of the square root of 2 was supposed to be related to what would happen if you had a planar map with the extra structure of a spanning tree. The special value gamma equals the square root of 3 was supposed to correspond to what would happen if you had the extra structure of an Ising model. And there are many other special values of gamma which correspond to other types of planar maps. And actually this one here, this corresponds to the planar map with the extra structure of something called the bipolar orientation. And somehow, you can see that this somehow looks fundamentally different from the uniformly chosen one. And the reason is that, a planar map with a bipolar orientation somehow wants to be more regular. And as a result, when you embed it into three-dimensional space, you see something that looks blobbier. Now, since the conjectures have been made, now a number of results in this direction have been proved. But in order to make these things rigorous, you have to somehow explain exactly what you mean. And the reason is that a priori, we're talking about two very different things. So random planar maps, you can think of as being metric spaces. That's something which is very concrete. But this expression here doesn't really make any sense. And so you have to figure out some way of making sense of what this means in an appropriate way so you can identify it with your scaling limit of your discrete object. And so what this talk is about is how you understand this formal expression for a Riemannian metric as corresponding to an actual metric. So you have a real distance function. And this is something which is natural to do because that's really what you have when you talk about random planar maps, because they're just random graphs. Okay, so now I want to say a few words about why people in probability theory got interested in these questions. And part of the motivation comes from something called the KPZ formula. And I'm going to explain to you how that works. So the idea is that if you had one of these random surfaces coming from exponentially in the Gaussian free field, then you would expect that you're not going to get something which is smooth. It's not going to be a smooth metric, but you could hope that it would at least be Holder continuous with respect to the Euclidean metric. And what this means in practice is that if you have some kind of a fractal drawn on top of your surface, if you calculate the dimension of the fractal using the Euclidean metric, it's not going to be the same thing as what you would have gotten if you had calculated its dimension with respect to this Liouville quantum gravity metric, because it is not going to be diffeomorphic to the plane. And there's a formula from the physics literature due to Kizhnik, Polyakov, and Zamolodchikov, which tells you how these dimensions actually transform. So here, the idea is that it's often easier, for some reason, to calculate the dimension of a fractal like this with respect to the random metric. And then what you get as output from this formula is what the dimension is supposed to be with respect to the Euclidean metric. And okay, so now let me explain a little bit about why probabilists were even interested in this formula. And there's kind of a famous example. So it has to do with planar Brownian motion. So this is just the range of a Brownian motion run for one unit of time. And one thing which is interesting to look at is the outer boundary of the Brownian motion. So this is the curve that I've highlighted in red. And there was a famous conjecture that Mandelbrot made back in the 1980s about the dimension of the outer boundary. So how rough is it? And he conjectured that the dimension is given by 4/3. So this just means that the number of balls of radius epsilon that you would need to cover this, this red curve would be about epsilon to the minus 4/3. Now, if you were to try to prove Mandelbrot's conjecture, and you think about it for a little bit, there's a very concrete thing that you would have to study. What you imagine doing is that you start off with a little disk of radius epsilon inside of the plane, and then you fire off a bunch of independent Brownian motions starting from equally spaced points on the boundary of this small disk of radius epsilon. And then you want to know what is the probability that the ranges of these independently run Brownian motions stopped at the first time that they exit the unit disk are actually disjoint from each other. So this is actually a rare event because it's very hard in 2 dimensions for ranges of Brownian motions to be disjoint from each other. So it's going to be very unlikely. And quantifying how unlikely it is turns out to be a surprisingly difficult mathematical problem. So how is this problem actually solved in practice? So the idea is that somehow the thing that makes this difficult is the fact that the underlying geometry that you're working on is fixed and it's rigid. And these kinds of questions become much easier if you make the underlying geometry random. It makes the combinatorics of the discrete version of this problem much simpler. And so what happened is that this physicist, Bertrand du Plentier, so this is a picture of Bertrand. This is the main topic that he works on. And so if you look closely at this picture, he's exactly talking about this topic here. So what he did is he looked at this question in the setting of a random quadrangulation. So he looked at a discrete version of it with random walks rather than Brownian motions. And then he came along and he solved it in a physics way. So he got a number. And then he applied this KPZ formula that I told you about just a moment, which converts the probabilities computed on the random geometry to the deterministic one. And then this gives you a prediction, because nothing was rigorous yet, for what the non-intersection probability was supposed to be for these Brownian motions. And then what happened is that the mathematicians came along, and in this case it was Greg Lawler, Oded Schramm, and Wendelin Werner, who proved these conjectures mathematically, but using a totally different set of techniques. So it wasn't about like, dotting I's and crossing T's in the physics derivation. They were doing something totally different using these Schramm-Loevner evolutions, which were invented by Schramm a few years before. And there were lots of other examples where exponents were predicted somehow using this sort of methodology. Mathematicians came along later using SLE techniques, and then they proved them using very, very different set of ideas. And so this subject sort of came about because people wanted to understand, whether or not we could make these techniques that people were using to guess exponents into rigorous mathematics. Okay, and I want to mention one other thing, which is where some of these conjectures about the relationship between Liouville quantum gravity, the continuous theory of random surfaces, and random planar maps came from. So what sort of happened is that back in the 1980s, when people were looking at these things, they realized that the way that dimensions transformed when you went from a random geometry to deterministic one was the same, both in the context of Liouville quantum gravity and in random planar maps. And this is something that Polyakov wrote about in a memoir that he posted to the archive back in 2008, From Quarks to Strings. And he has this quote where he says, a few years before this work, Kazakov and David suggested that the discrete version of gravity should be described by the various matrix models. So what he's saying here is that the right way to discretize Liouville quantum gravity is using matrix models. This refers to random planar maps, because one way to count different types of random planar maps or planar maps is using random matrices. And then he said it was really hard to know whether or not this could possibly be true. But then once they realized that dimensions transformed in the same way, both for planar maps to the square lattice and also Liouville quantum gravity to Euclidean space, that was sort of enough for him to have no doubt in his mind that the continuous Liouville quantum gravity surfaces were equivalent to the scaling limit of random planar maps. But of course, from a mathematical perspective, this is really, really weak evidence to know whether or not this conjecture should be true. Okay, so now I want to go back to Liouville quantum gravity and talk a little bit about how do we make sense of these things rigorously as mathematicians. And we have a formal expression for a Riemannian manifold, Riemannian metric. And whenever you have a Riemannian manifold, you want to be able to understand things like the volume form. So how do you measure areas, and also a distance function. So how do you calculate distances? And it turns out that for this formal expression here, even though it doesn't make any sense, it's actually quite straightforward to define what should be the volume form. So here, the difficulty again is that we're exponentiating this distribution, which doesn't make sense. And the most natural way to get around that problem is to replace the Gaussian free field, the distribution, with a regularized version of it. A very nice way to regularize it is to consider what happens when you average it on the boundary of a ball of radius epsilon. And then he just showed that you can take a limit as epsilon goes to 0 of the regularized version of the associated measure. Now, when you take this limit, you have to introduce a normalization factor. So there's this extra term, epsilon to the gamma squared over 2. And where this comes from is that it's very easy to calculate the variance of the circle average of the Gaussian free field. And the main term is the log of 1 over epsilon. And so when you introduce this factor here, this is what you have to put in so that the expected amount of area remains finite. And there's actually a number of different works where these measures were made sense of. The first one that I'm aware of is due to Hooke-Krohn. It's also closely related to Kahan's theory of Gaussian multiplicative chaos from the 1980s. And then there was this paper by Duplantier and Sheffield from about, let's say, 15, 17 years ago, which also contained a construction of these measures. And this paper was really important in the subject because this is one of the works which really popularized it and made it into what's now a big topic in probability theory now. Okay, but the metric, the distance function, is sort of a different story. And the reason that constructing a metric is different from constructing a volume form is that somehow a volume form or an area measure just locally depends on your Gaussian free field, your conformal factor. But if you want to know about distances between different points, somehow you have to consider an optimization procedure which optimizes lengths of paths across your entire domain. And in the subject, before this work that I'm talking about today, the metric was only constructed for one very special value of gamma, the value where gamma is equal to the square root of 8/3. And in this case, the construction was something which was actually quite indirect. So it wasn't based on an approximation procedure. Basically, what we did together with Scott Sheffield is we defined a sort of growth process, so something which is sort of growing on top of the surface, which turned out to describe the growth of metric balls on a metric that you could put on the surface. And this was somehow done quite indirectly using SLE. But the sort of natural way to think about this is in the same spirit as the volume form, where you do an approximation procedure, where you take your Gaussian free field, you regularize it in some way. Once you've regularized it, it's not that difficult to define an approximate notion of distance, where you just infimize over the lengths of all paths computed with respect to the regularized metric. And then you could try to understand what happens when you take a limit as the regularization goes away. And this turns out to be something which is challenging to look at. And this now has a name in the literature. This is called Liouville first passage percolation, because it's like a first passage percolation model where the weights come from the exponential of the Gaussian free field. Now, one thing I want to emphasize is that there's some subtlety here in terms of what number you put inside of the exponential. So this is supposed to be for a gamma Liouville quantum gravity surface, but it turns out that when you build the metric, you don't actually want to put gamma here. The correct thing to put is this exponent, which is now called psi, which is given by gamma over d sub gamma, where the d sub gamma is the exponent which determines the growth of volumes of balls inside of this metric space if it were known to exist. Okay, so what happened in the subject is that this model, Liouville's first passage percolation, this was first considered by Ding and Dunlap. And what they showed is that when the parameter gamma is very small, if you take this proxy for a distance and you renormalize it, so they just renormalized it by the median. So they didn't know what the normalization factor should be, but you could always normalize by the median. And they proved that what you have is tight. So you have subsequential limits. Then a little while later, another group, Dubada and Falconet, came along and they proved another tightness result. in their work, they had a slightly larger range of gamma values, but their work also had some other very nice features to it. So they had some very nice arguments, which are very useful for later things. Then a little bit after them, Ding and Dunlap came back. They introduced a different approximation procedure called Liouville graph distance and proved that you have tightness for the entire range of gamma values. And then these two teams got together, so Ding, Dubada, Dunlap, and Falconet, and they proved tightness for this approximation procedure for the entire range of gamma values. And somehow, this one is a little bit nicer than this one when you want to actually prove things about the subsequential limits. Okay? Just to give you a sense as to what this exponent actually looks like, here's a plot of psi as a function of gamma. So it's gamma divided by d sub gamma. On the horizontal axis, I have the gamma values here, and this is psi. So what values does it take in practice? So when gamma is equal to 0, the value of psi is equal to 0 because it's just the Euclidean metric. And then some of the other interesting values of gamma, like the square root of 2, square root of 8/3, and square root of 3, they all have a psi value, which is about 0.4. But actually, one of the big outstanding questions in this subject is people don't know what the explicit number is for d sub gamma, except in the very special case that gamma is equal to the square root of 8/3, where it happens to be 4. Okay, and so what is the new theorem? Well, it was new when we proved it, together with Hewen. So we showed that if you have a Gaussian free field and gamma between 0 and 2, which is fixed, then these approximations, which were considered in the works I mentioned just a moment ago, they don't just have subsequential limits, they actually have a true limit. And you get this limiting metric that you can associate with your free field. And then you could ask, why is this really the right object to look at? And this was also part of the mathematics. So we showed that it's somehow singled out by a minimal list of axioms that any natural metric associated with the free field would have to satisfy. So I'll explain what this means more formally in just a moment, but loosely speaking, the metric has to depend on the field in a local way. It has to give you something which is homeomorphic to Euclidean space, and then it has to satisfy some kind of a transformation rule when you apply a change of coordinates. And this construction, it's very different than the previous one, when gamma was the square root of 8/3, but we know that we get the same object that was constructed before in this case, because the square root of 8/3 metric from before also satisfies these properties, and there's at most one metric up to a multiplicative constant which satisfies these axioms. Okay, so that's the theorem. Let me just make a few comments about it to compare it with the earlier work. So as I said before, in the case that gamma is the square root of 8/3, the metric was constructed in an indirect way. So we somehow built a growth process, which is like an Eden model on this random geometry, using SLE6 processes, for those who know about it. And the proof, somehow relied on lots of magical special properties that SLE6 has when you consider it on top of Liouville quantum gravity. In particular, there are many formulas that come up because you see lots of Levy processes where you can do computations. And these exact formulas were also quite important because this is what made it possible for us to show that this metric is the same as the Brownian map, the one that comes from the scaling limit of uniformly random quadrangulations. But the metric for general values of gamma, it doesn't make use of any SLE techniques, so there's no magic coming from that subject. It's somehow based entirely on elementary estimates, elementary techniques and ideas just using the Gaussian free field. And the starting point is this, again, the definition of a Liouville quantum gravity metric, because that tells us what we're aiming for. And again, what this is it's just a minimal list of properties that any metric that we naturally associated with Liouville quantum gravity should have to satisfy. One thing which is also quite different about this is that in the case that gamma is the square root of 8/3, you know what the metric space is that you're aiming for because it's supposed to correspond to the Brownian map. And in that case, there's a very explicit construction of it in terms of something called the Brownian snake, which is something that you can build out of Brownian motion. Whereas for general values of gamma, there's no alternative construction of the object. At the same time, it's not like this work replaced the work that was done before. And the reason is that in the general framework, you don't really see that the square root of 8/3 is special. In particular, it doesn't seem like it's really possible to make a connection to different types of random planar maps without using the SLE-based tools. So that's something which is important. Okay, so now I just want to explain a little bit what these properties are that single out the Liouville quantum gravity metric. And one of the important things comes from the way that you do a change of coordinates in this subject. So just to remind you, how is the volume form defined? The volume form is defined just by regularizing the free field and then renormalizing it by the factor epsilon to the gamma squared over 2 and taking a limit as epsilon goes to 0. And because you have this extra renormalization factor, the version of the coordinate change formula that the measure satisfies is a little bit different from the normal Jacobian determinant formula that you have in calculus. So in particular, if you start off with a planar domain, like this one here, and you have a field on it, which is defining a surface or a volume measure, then if you want to map that field to another domain, let's say d tilde, if you want the volume form defined by the mapped over field to correspond to the original one, in the sense that if you take a region here and then ask, you want its sort of area to be the same as the mapped over area, what you have to do is you have to add to your field this number q times the log of the derivative of your conformal map. So q is 2 over gamma plus gamma over 2. If we were working in normal smooth geometry, you would have the 2 over gamma term here, because 2 over gamma times gamma is 2, and the extra term that you get is the gamma over 2, 1, okay? And the idea is that, the field is supposed to be describing a surface, and when you map it over to a different domain and you correct the field using q times the log of the derivative, then you're just getting a different parameterization of the same surface, okay? So this is just a variant of the usual coordinate change formula from calculus with an extra correction to reflect the fact that this is something which is fractal. Okay, and so what are the axioms which single out the Liouville quantum gravity metric in slightly more detail? So first, what we need is something which is homeomorphic to Euclidean space. So in this case, if I'm working on the whole plane, I have something which is homeomorphic to C, the complex plane. And we assume that it's a length space. So this just means that if you have 2 points Z and W, then there's always a path which connects Z and W, and its length is within epsilon of their distance. We could have assumed it was a geodesic metric, but this is a slightly weaker axiom. Then there's the locality axiom, which says that if you have any subdomain of the complex plane, then the internal metric on the subdomain, which is induced by our metric on the whole plane, this is just determined by the restriction of the field to the subdomain. Then there's something called Weyl scaling. So what Weyl scaling says is, if I take my field and I add a constant to it, then the way that distances are changed is by just multiplying their distances with respect to the original metric by the factor e to the xi times c. So this is something which is very natural because this just has to be true from the way that the approximation procedure was constructed. And the last thing is the compatibility with coordinate changes. So when we perform a coordinate change and we have a conformal map and then add q times the log of the derivative, this is supposed to be just another parameterization of the same surface. And so it should be true that the distance is preserved with respect to coordinate changes. And the reason that it's phrased the way that I've written here on the slide is that actually for the proofs of things, we didn't have to assume that this was true for all conformal maps It only had to be true for scalings and translations. Okay, and actually, where did this definition come from? It came from an earlier work that I had together with Wei Qian, where we were looking at the structure of geodesics in Liouville quantum gravity. And there was this question as to how these geodesics were related to SLE. And at the time, there was only a square root of 8/3 metric. So we were working with the square root of 8/3 metric and asking how do these geodesics relate to SLEs. But then we sort of realized that we didn't really want to use any of the special properties of the square root of 8/3 metric. It somehow was going to work more generally. And so we wrote down a very similar list of properties and said, if a metric existed, then the geodesics, had to be singular or somehow different from SLE. Okay, so I'm going to finish now by just making a few final comments. So first of all, what I've described to you today is just a pretty small part of this subject. So it's grown in many different directions. In particular, there is a huge part of the subject which looks at different types of random planar map models. So people ask about, how do you enumerate these things? How do you count them? What are different types of bijections that you can prove? And people still continue to develop these types of things for many different types of planar map models. This is what people do more if they have a combinatorics background. There are some people that are at the interface of combinatorics and computer science that look at these types of things. There's also been a huge part of the subject which has been aimed at exact computations. So computations of things like correlation functions. So if you came to the talk on Tuesday by Remy Rode, he showed some absolutely amazing formulas that people have been able to prove about like the 3-point correlation function. This is the DOZZ formula, and also formulas for higher order correlations. This is something called the conformal bootstrap. And then there's been another line of research where people have used these things to prove lots of very interesting things about SLEs. So if you came to the talk that Shin Sun gave yesterday, he talked about new amazing formulas proving long-standing conjectures about SLEs and models related to SLE, like the percolation model, using random surfaces from Liouville quantum gravity and these exact correlation functions that were computed by people in Remy Rode's group. In terms of the metric, what kinds of other things have happened? So the work with that I just talked about was focused on what's called the subcritical regime, which means that gamma is strictly smaller than 2. Then you could ask about what happens when gamma is equal to 2. And in this case, the metric was constructed by Ding and Nguyen. And here you get something which still has the Euclidean topology, even though it's critical. It just turns out that there are lots of really interesting and challenging things to do, because somehow the metric that you get is no longer Holder continuous with respect to the Euclidean metric, and this introduces lots of challenges. And then they went beyond this, and they considered what's called the supercritical regime. This is when psi is bigger than the value that you get in the critical case. And Ding and Nguyen also constructed a metric here. And then it starts to get really interesting because you don't have a geometry which is Euclidean anymore. You get something which has a non-Euclidean geometry. So it's not homeomorphic to a planar domain. One of the big outstanding computational problems in the area is to calculate this d sub gamma, this volume growth exponent. It's not known what it's supposed to be, but there have been some predictions. One of the first well-known one, which is due to Wadabiki. This was made back in the 1990s, and he guessed that the dimension was supposed to depend on gamma in this way here. This is correct when gamma is equal to 0, because if you plug 0 into here, you do in fact get 2, the dimension of Euclidean space in 2 dimensions. It's also correct when you plug in square root of 8/3, because in that setting you also get 4. And people had wondered for a long time whether or not this was actually the correct answer, but it was disproved by Ding and Goswami, at least when gamma is small. So what they did is they showed that when gamma is very, very close to 0, the way that d sub gamma behaves does not have a quadratic correction. It has a correction with an exponent which gives you something which grows more quickly than a quadratic. So the exponent is smaller than 2. Now there's a new prediction, which is due to Ding and Gwyn, and their guess is that maybe it looks like this. This also agrees when gamma is equal to 0 and gamma is equal to the square root of 8/3 with the known values. It seems to be close to simulations. People have done some very careful simulations and plotted these two things. And yes, this seems like it could be correct, but in general, no one really knows because there's really no reason to expect that you would have such a simple formula. And then in my own work, following this, I've been looking at trying to construct different types of metrics in other settings. So still, involving planar fractals, but different types of fractal geometry, in particular involving things called conformal loop ensembles. So conformal loop ensembles are kind of like random analogs of like a Sierpinski carpet. This is like a random analog of the Sierpinski carpet or the Sierpinski gasket. And these kinds of things are interesting because they describe scaling limits of other things that people look at in statistical mechanics in 2 dimensions. So in particular, these types of things describe the scaling limits of the interfaces in things like the Ising model in this regime. And in this regime over here, you get things that describe the scaling limit of objects like critical percolation. And so we try to understand what kind of metrics that you can build in this setting. Here, the mathematics is quite different because these are not Gaussian models. They're defined in a very different way. And so this introduces a lot of interesting challenges that we've been looking at recently. And I want to finish by showing you 3 more pictures that I actually just found yesterday. These were taken from a paper by Barkley and Budd. So Budd is somebody who's been involved in doing a lot of really interesting simulation work in terms of dimensions and other types of quantities. And he had some pictures in this paper that I hadn't seen before, which again show you what these random surfaces look like for different values of gamma. So this is the square root 2 case. This corresponds to what happens when you have a spanning tree. This is blobbier than the case with, which is just uniformly at random. This one corresponds to the square root of 4/3. This is a bipolar oriented one, which is even blobbier. And then there's the one which is sort of most blobby out of the ones that I have is the one which corresponds to gamma equals 1. And here there's another structure on top of it, which comes from these sort of 2-dimensional models. In particular, it has an instance of something called the Schneider wood on top of it. Okay, so that's what I wanted to say, and I will stop there. Thank you. Yeah, I mean, so the techniques in terms of constructing the continuous object, as long as it's sort of like locally kind of like the Gaussian free field in some way, then all of the techniques will work. So you choose. Yeah. So the main thing is that it has to be a log correlated field, and the multiple in front of the log determines like what type of gamma that you're going to get in the limit. So as long as it's sort of like locally absolutely continuous with respect to the Gaussian free field, then everything works. And actually, in reality, the right fields to work with are not the Gaussian free field. They're things that are related to it and come from it. If you make if you consider other types of log correlated Gaussian fields, then less is known about actually constructing these limits. And actually, there's been some very interesting work which shows that if you do make a strong enough microscopic perturbation, you can get something which is quite different. But in terms of the mathematics that one actually wants to do, really the Gaussian free field is the right thing to look at because that's the one, or the right variance of it that will correspond to these types of discrete models in the scaling limit. Yes. So there was one, yeah. So what happened is that um, in this general regime, the tightness results were proved by these people. They showed that you can take subsequential limits, and then we showed that there's at most one limit, so it's unique. And then there was a previous work which was just focused on the case that gamma is equal to the square root of 8/3, where we showed that it was the Brownian map. And then we know that the square root of 8/3 previous construction is the same as the square root of 8/3 new construction. So that's not been shown. So convergence results have been proved in other topologies, different types of topologies that have to do with the bijective encodings of the other types of discrete objects, but metric convergence has not been proved yet. No, so it's not special at all. It makes absolutely no difference. Yeah, so I think the results that you would call surprising to physicists, which have come out of this, or could be surprising to physicists, is in this direction right here. So, well, no, so there are, so I meant this new SLE results. So in the physics literature for percolation, for example, they had a guess as to like what would be, the one arm exponent or the arm exponents when you have an even number of arms. But there was a very recent work which computed something called the backbone exponent. That's when you have two disjoint arms. And there was no physics prediction as to what it was supposed to be. There were some numerical simulations. And then using the guess that exponents are always rational in this subject, there was a guess that maybe this was a rational number. And then there was this recent work that Shin Sun talked about yesterday, where they actually computed the exponent rigorously. So there was no known value from physics before. They computed it rigorously, and it's a transcendental number. And I think that would be something which would be a surprise to physicists.
Yeah, so the new prediction of the green, so we now have more evidence that it is the or
So the evidence is that it satisfies the rigorous bounds. So there are rigorous upper and lower bounds. It's in the middle. It's quite close to the numerical predictions. So the curve is close enough that it's within the error bars. And beyond that, I think the only other piece of evidence is that it's kind of a nice function. But I think that's why we typically refer to it as a prediction and not a conjecture, because that's a weaker statement to make. It's based on an application of the KPZ formula. I mean, the mathematical proof that it's wrong is just in the bound. And there's actually no reason to expect that the KPZ formula would be applicable in this setting. He just applied it and then guessed that it was, it could be correct. I didn't say that. I didn't say that. It's just that, in these kinds of things, this is a very nice number. And there's no reason to expect the numbers to be so nice. So I don't know. Yes. Basically, everything is sort of different in terms of how the mathematics works in terms of these things. It's just sort of a different object defined in a different way, um, with a sort of different motivation in some sense.
thank you very much.